without further ado, I'd like to introduce Dr. Shaoliang Guan, who's joining us from the Maxwell Centre just over the road. He's based both here in the Cavendish and at the Materials Science Department, and whilst he has a background in chemistry, he's very much part of our physics community now, and he's here to talk to you about materials and surface matters.
Thank you very much, Jacob. Thank the organizer inviting me to give this lecture. I'm really honored. So, if you're aware, yesterday was the International Day of Women and Girls in Science. So, hope all of you had a great day. So, I'll first introduce myself. Of course, I came by plane from China to UK. I wish I brought the sunshine with me, but I didn't. And the first stop was in Belfast when I did my master's degree in chemical enzymology. Then I moved to Cardiff to do a PhD in electrochemistry. I spent a couple of years in Glasgow for my first postdoc. And before I moved to Cambridge, I did a few more years in Oxford, which actually is a Harvard campus. So finally I'm here, and I've been in all the countries in UK, and I'm really pleased of the experience that I have. So without further ado, I'm talking about the main topic today, which is surface matters. So when we talk about the material, we instinctively imagine its bulk, the strength of steel, the transparency of glass, and even the conductivity of copper. But the truth is that the surface that meets the world first is the very first layer interact with light, heat, chemicals, other materials, and even living cells. So change the surface, you often change the entire behavior of the materials. So today we are going to learn some materials, not just as the static chunks of matter, but as the dynamic systems whose surfaces determine how they behave. If you understand the surfaces, you start to understand how materials succeed, fail, or transform. Hence the title. It's also the title of the Surface Matters when we had this stand in the Royal Society Summer Exhibition Summer Exhibition in London in 2019. So if you went to that exhibition 7 years ago, probably you have seen me dressing like this, holding a gun. But it's not a real gun, it's an X-ray gun. So the name is bond, but it's covalent bond. Later I'm going to explain why it's covalent bond. So why does surface matter? And why is gold shining? How smartphones work? And what did Albert Einstein win the Nobel Prize for? We're going to discover them together for the next 1 hour. First, let's look at this elephant. It's huge, right? How many atoms in total and how many atoms on the surface? I can count the zeros, but I can tell you that there's only a tiny bit of amount of atoms on the surface. If we go down to a smaller object like bacteria, it's about 1 micrometer in diameter. Normally, the human hair is around 100 microns. So now, if we work out the atoms on the surface, it will be 0.07%. Can you think of something even smaller? What, nanoparticles? So this is platinum nanoparticles. It's a 5 nanometer in diameter. It's often used in catalytic converter. So if one of you drives diesel car today, there's still a catalytic converter inside of the diesel car, which converts the poisonous gas to neutral ones before it can be emitted to the air. So it's small, but if we count the atoms on the surface and compare it to total atoms, I think some of you already work out there are nearly 30% of all atoms on the surface. So the surface matters at very small scale, we all know that. Again, let's look at this gold in the water. Normally, gold is very stable. It's resistant to oxidation. But if we make very tiny nanoparticles from gold, first, the color starts to change from either to red or purple. This is because of the local resonance of the nanoparticles and absorbing the light and in different wavelengths and give us reflect the opposite color. It's also very reactive. That's why researchers start using gold nanoparticles as catalysts or functional materials. Researchers can make gold, all kinds of shapes of gold nanoparticles and apply them to many fields. For example, they use the gold nanoparticles to target the cancer cells in the photothermal therapy, or they make the acetylene and hydrochlorination process, which is a building blocks for plastics. And there are also other functions. So we know that the surface matters in very small scales. It seems far to us, but it also matters in the palm of our hands. We all have some smartphones like this, right? So when I was at your age, I probably used one of these. But how do smartphone work? We talk about the mobile processors, the memory components, and the sensors. And we care about the batteries, hopefully can last longer than one day. And in this smartphone, there are some key materials, which one of them is semiconductors. So today I'm going to talk about materials, mainly focusing on the semiconductors and their surfaces. So I only mentioned one type of semiconductors called transition metal dichalcogenides. You can call it TMDs. So it's a type of atomically thin layered MX2 type of semiconductor with one layer transition metals sandwiched by two layers of chalcogen atoms, as you can see here in the periodic table. So unlike graphene, the TMDs have semiconducting characters with an electronic band gap. So their unique properties can lead to wide applications in high-end electronics, spintronics, and optoelectronics, and even DNA harvesting. So they look like this, which has this kind of MX2 form. Then they can be stacked layer by layer. And the researchers can make very thin layers, just a monolayer as well. So here's a map, shows that the applications of the 2D materials-based technology integrate with time and complexity. So the size of the circles is a rough estimate of the market opportunities. And their positions indicate when the first products were or could be potentially introduced. So we've seen some sensors that integrate with 2D materials. And you may be more familiar with some augmented video game or VR type of games. And nowadays, the electric cars give us this, require this light detection and ranging ability as well. So they are used in optoelectronics field as well. And researchers in Cambridge, they found that this type of single photon emission is very quite excited in the quantum technology field. But this single photon emission has been seen randomly and appeared in the materials. The researchers in Cambridge discovered that if they build this kind of pillars on the substrate, then cover a monolayer of MX2, which is TMD sheet, like tungsten selenites, then they can control the emission in a controlled fashion. Also, there are lots of interest in this kind of monolithic 3D integration with different 2D materials with different applications. So the technology is promising and potentially we can use them. But how do we make this kind of materials? Here I only introduce one type of thin film deposition method, which is called chemical vapor deposition. So the CVD approaches are very promising in this context. And here it shows this growth process of this 2D TMD, which is classified as 4 categories. We have the metal precursors and the chalk gem precursors. And depending on how much the mass flux is, we can make either continuous polycrystalline and 2D materials or the discrete single crystalline materials. So there's one example here. We're looking at this process, which is using sodium tungstate reacting with sulfur to form this tungsten disulfide and TMD materials. And we use this scanning electron microscopy to visualize the growth of this material. So if you look at this diagram, the picture here shows that there are sodium tungstate particles deposit on the sapphire surface. And if we heat the substrate, it will melt. Then by shining the electron beams on the particles, we will collect the secondary electrons, which give us the picture showing here. And the color represents the color change depending on the atomic numbers of different elements. So let's look at this video if we can. So pay attention that it's in very small scale, 10 microns. With the temperature ramping, we'll see that this sodium tungstate start to melt. So once it reaches 700 degrees C, it totally melted and spread across the surface. So what is this halo-like materials on this substrate? We need to find out. So we capture different stages of these materials, and we'll find out that the sodium tungstate can melt and form different ratio of combination of sodium oxide and tungsten oxide. And with different temperature, the ratio between them changes. And here marks at different positions, there are different amounts of each of these compounds. So how do we confirm those elements are actually on the surface in the halo? We use another technique called X-ray Photoelectron Spectroscopy. We can shine the X-ray with the 20 micron size on the halo at different spots. We'll collect the information. If there are tungsten or oxygen or sodium, it gives us some peaks which indicate their presence on the surface. So we can see that across from position 1 to 5, the peak intensity are changing, with the 3, which is in the middle, in the center, has the largest concentration. So once we have this metal precursor, which is tungsten oxides, we want to introduce sulfur because we want to build this sandwich-like materials, 2D materials. So we introduce sulfur by injecting the gas phase of dimethyl disulfide at 700 degrees C on the same halo spot. Let's see what will happen once we introduce sulfur. This is a nozzle spreading the gas to this surface. We start seeing the flakes growing inside of the halo, and they become bigger and bigger, and there are probably some dots around outside the halo as well. So now the flakes have been formed. Can we confirm that's the product, tungsten disulfide, we want? So the third technique, just briefly introduced, which is called transmission electron microscopy. And from the top view of this surface, we can see that with the passage of time, we build something more on the surface, and there are flakes above them. And from side view, which is cross-sectional TEM image, we could see that there are thin layer of tungsten and sulfur on that surface. Now the scale is nanometers. And we can confirm that a thin monolayer of tungsten disulfide have been formed in this, on top of this sapphire surface. So with the combination of different techniques, we could confirm what we want and what we have made. So skip the other two techniques. Today I want to focus on the X-ray Photoelectron Spectroscopy, or XPS. And what can it do? It's a surface technique to study solids, metals, powders, and even liquids. It's a quantitative method, and so that we can identify those chemical composition and chemical states. Nowadays, with the development of the technique, we can use argon ions to etch the surface so that we even can see the bulk layers underneath the top surface. So this leads to us the third question: what did Albert Einstein win the Nobel Prize for? First, I will introduce the history of XPS. So in 1887, Heinrich Hertz first discovered the photoelectric effect by shining light on the surface. Then in 1905, Albert Einstein formally described this phenomenon, and he won the Nobel Prize in 1921. It's not the general relativity, though. Then in 1914, Robinson and Rawlinson first discovered the photo effect using X-ray, which is more powerful, more photoelectrons. And not until 1951, Steinhardt and Surface first used this technique as a chemical analytic tool for their research. So the bulk work done by Kai Szechuan from Uppsala, which contributed to the modern XPS instruments that we are using today. And he won the Nobel Prize in 1981. And exactly 100 years after the first discovery of photoelectric effect, I was born. So the first time I got to know the XPS was 2014, when I was in Cardiff University. It was an elegant XPS STM combined system. Oh, here's another picture. That's me showing my newborn baby what's it like. They say it's never too early to start learning science, right? So 2 years ago, I moved to Cambridge and running all the XPS facilities here. So between the last two Nobel Prizes, there was a 60-year gap, where there'll be another Nobel Prize in 2041. Maybe one of you will soon discover something using this technique in the future and win a Nobel Prize for us. We'll see. So what is XPS like? There are many manufacturers shown here. And we have this one, and this one, 3 XPS instruments in Cambridge. They may look different, but the basic principles are the same. So when an X-ray source, usually coming out from aluminum, magnesium, or silver, shines on the sample, and the electrons will absorb the energy and being kicked out as photoelectrons, which are collected by this electron energy analyzer. So the X-ray may penetrate dozens of microns through the surface, but only the top 10 nanometers, where the photoelectrons come from, have the characteristics information, which give us the elemental information. Again, if we look at the atoms, when X-ray shines on the electrons, they will escape from the orbital, become photoelectrons. Each electrons have their original binding energy, and we are measuring the kinetic energy, which is the speed of the electrons from this analyzer. And we know the X-ray source energy. We'll be able to work out their binding energy in their orbitals, hence determining the elements where they are from. So here again shows that in the XPS spectrum, we can see that there are peaks from the same element, but from different orbitals. This is because any of the electrons that can absorb the certain amount of energy, and if there's enough energy, they will be kicked out. So there are different peaks from different orbitals in the same element, but the intensity and the positions are different. So this is called the cross sections or relative sensitivity factor, determining how easy those electrons from different orbitals can be escaped. So why is this a surface technique? It's actually a low energy and X-ray source, which is 1.5 keV, comparing to the medical CT you see in the hospital. That's about 60 keV. So that's much stronger, so you'll be able to see your whole body, your skull, etc. But the X-ray used in XPS has low energy. So those electrons buried deep in the bulk will absorb the energy. However, it's difficult for them to travel through the bulk. They get scattered by other atoms. So only a few electrons can get out unscattered and detected as the peaks. many more loose energy making up the background. So these are all the electrons which don't have the exact energy as them. And the vast majority don't get out, actually. So it's halfway through the lecture. I would like to have a quiz time. So this is a short video I made. Nowadays, I think, and we use a lot of, we see a lot of videos in TikTok because we don't have patience to see 2 minutes video or even longer. So I made it very short, only 30 seconds. So during those 30 seconds, please pay attention to see if you grasp as much information as you can. You ready? Let's go. Okay, I spent 5 seconds on buy. So, what did you see? You can name anything you have seen, still stay in your memory. Yeah? Well, that's great information. Yeah. Yeah. That's very accurate. All right, I'm not going to play the game. So, yeah, we saw another name of XPS, which I mentioned before, right? The ESCA, electron spectroscopy for chemical analysis. It's a very awkward name. That's why we don't use it anymore. We call it XPS. So a molecule, which is, ESCA molecule, we call it. Carbon, binding energies, and something is greater than something, right? So let's look at this carbon atom structure and the molecule formula and the spectra again. So imagine those electrons circling the nucleus in the orbital. And if those electrons are apples, for example, and in this molecule, we have 4 carbon, 1, 2, 3, 4 carbons. But they are binding with different elements. This carbon is 3 hydrogen, this carbon, oxygen, oxygen double bonds, and carbon fluorine, right? So imagine I'm the first carbon holding an apple. You want to try to take the apple from me. It's quite easy, right? If 2 of me holding 1 apple, it's a bit more difficult for you to take the apple from me. So the second carbon has a higher binding energy than the first one. Now we have carbon-oxygen bond. So if I ask for help, for example, from Hulk, I think it will be much more difficult for you to take that apple from me. So this carbon has even higher binding energy. So who is stronger than Hulk? Well, even Incredible Hulk. So he's the fluorine, and this carbon has the highest binding energy. So this means that the electrons surrounding this carbon is the most difficult to be taken out. So XPS can be used to analyze many samples. And there's charts showing here. And I'm fortunate to get involved in many samples. And normally the XPS spectrum looks like this. It's a wide scan, including binding energy from 0 to 1300. So any electrons that have binding energies less than 1300 will be kicked out, and then they will be collected by the analyzer. We can see that there are carbon, oxygen, silicon, and silver, and their concentration has been listed as well by calculating those intensity of those peaks. Also, even for the silver, we have different electrons from different orbitals. So these are called core lines of XPS, and many characteristic features can help us explore more regarding their environment and oxidation states, etc. So today I'm going to talk about the chemical shift, just like I just introduced in the short video. If you have just learned from the video, another quick quiz here to keep you awake. If we look at the tungsten dioxide and tungsten trioxide, which electrons from tungsten has the higher binding energy? Yeah. Are you confident to explain a bit more? Why is trioxide? Yes, 3 oxygens. They all hold the electrons together, make the tungsten become 6+ in the oxygen states. Therefore, the electrons are more difficult to be removed. That's correct. So if we compare the tungsten trioxides and the tungsten fluorides, which one has the higher binding energy? Yeah, that's correct. Fluoride is more electro and negativity. So together they hold the electrons tighter, which let the electrons more difficult to be ejected from the orbitals. So we can do the plot like this. So I spent 2/3 of the time to talk about the surface. Is this only the surface that matters? We are going to look at from surface, dive into the bulk of materials and see what we actually can use this technique to study the modern research and in material science. So researchers would like to make any kinds of films and with different elements, and then they just put together to see what kind of performance they can get. Also, when they put together their compositions between the surfaces and between the layers may change. And sometimes we can use this technique to remove surface contaminations, which we don't really, which may give us the negative results. Let's look at the example of this architectural glass coating from the shard. It's a huge building all covered with the glass. As I introduced that the modern techniques allow us to use argon ion clusters or to bombard the surface and etch them layer by layer until we see something beneath the first layers. So how to read this diagram? If we look at from left to right is the outer surface of the glass to the bulk. Before we start etching, we can see there are 3 elements: oxygen, silicon, aluminum. So this kind of aluminum doped silicon glass protects the glass from wear and tear and extend its longevity. If we start etching a little bit, just over 50 nanometers, we start seeing there are only titanium, nitrogen, and oxygen left. So this layer, very thin, maybe 5 to 10 nanometers, is a low emissions material coated in the glass. It is transparent to visual light, but block a significant amount of heat. Move to about 100 nanometers beneath the surface. There's only titanium and niobium left. So this niobium oxide, it's a niobium oxygen left. So the niobium oxide is a good humidity barrier coating for the glass. It has a high resistance to electrochemical corrosion. Then another layer of titanium nitride. And finally, after 150 nanometers beneath the surface, we see the normal glass, which is silica. So although it's very thin, and we even cannot imagine if the scratch, everything will be gone, but it has all the applications and for each of the components. I'll quickly go through how the technique works. So basically, we can etch the surface with the argon gun, then X-ray source, collect the data, information, then etch again, collect again, so we can see from the surface layer till the bulk. And researchers here in materials department, they try to make some thermal barrier coatings and use elements including yttrium, zirconium, and scandium. And the bottom spectra we collected is the surface. Then we etch 14 times. We see the trend of increasing of scandium, for example, then decrease again. And also other peaks start appearing. So researchers really can make the films and stack them together. But it's the XPS which can quantify and measure if they have the right films with the right thickness. So there are two ways of etching the surface. One is called single atomic ion beam from argon. You imagine it's a bullet can penetrate deep into the inorganic material. But for organic materials, we use a little bit softer cluster ion to gently etch the surface because organic materials are more fragile. So in this polymer study, we use this type of second type of etching methods to etch polystyrene and the PVP. They are the layers, 50 layers, multi-layers stacked to each other. We can see that polystyrene only has carbon in it, but PVP has carbon, nitrogen, and oxygen. So we can see the oscillation of those element concentration when it reaches either in the PS layer or in the PVP layer. They are both important materials for plastics manufacturing or the water-soluble materials. So XPS, of course, is important, and materials as well. And are there any applications that are close to our daily life? Of course, there is. For example, it's quite popular now about installing the solar panels on the house roof, especially these new built ones. They have the in-roof solar panels already fixed. So usually in the UK market, we have this 1 kilowatt system and for the households, which they can usually generate 800 kilowatts hour per year. And it's a size of 7 meters square, which compose of 4 pieces of those solar cells. So for example, personally, in my house, I probably use 2,400 kilowatts hour per year, which means I need to install 12 solar cells on the roof, and if they generate that amount of energy per year. But also you need to pay attention that it's not giving us this energy every day. When in winter, still we need the electricity. And there are two types of materials that we can use for the households. One is called monocrystalline silicon, which is play the major part in the market. It has the high efficiency, reaches up to 23%, longer life, like 25 years, but higher upfront cost. There's another called polycrystalline silicon, medium efficiency, 18%, slightly lower initial cost. So just for your reference, if you want to install one of these. But there's also the third type, which is called thin film solar cells. Although it has low efficiency, shorter life, but it's light and flexible, and they're mainly used in industrial scales. This is a cross-section image of a thin film solar cells called CIGS. It takes from these layers, which is copper, indium, gallium, and selenite. When the sun shines on the layer, and if we look at the scale again, it's 1 micron, just very thin surface and layer covering on the glass. That's what the solar cells mainly is. And the sunlight shine that, give us electrons, then we can collect the energy, electricity, and for us to use. Again, if we look at the steps profiling of these solar cells, there's a zinc oxide on the surface to prevent the wear and tear. Then this cadmium sulfide is a p-n junction, very thin layer for this semiconductor purpose. Then another 500 to 1 micron depth of this main semiconductor part. Again, the researchers in Cambridge started looking at even more advanced solar cells, which is perovskites. And there's very complicated chemical formulas on top of different layers. We can use the same technique to study their uniform layers between each of them, and even identify if they are at their right chemical environment. For example, their oxidation states. The last application that I want to introduce is lithium-ion batteries, which is also very popular. And they look like this in a manufacturing workshop. They're very big, large, and then we cut to very small pieces and folded them to form this kind of batteries inside our phones. But if you look at this phone, that battery has been swollen, which means it's not safe to use anymore. Sometimes it can catch fire as well. So what is actually happening in this is when the lithium-ion battery discharge, the lithium metal will lose electrons, become lithium ion. They will travel through this membrane to this side. The outside will create a electron current, so that provides the electricity. But once it's recharged, those lithium ions will come back to gain electrons and become lithium metal again. Those lithium metal sit on the surface of lithium site. And if there are hundreds or thousands cycles, those lithium metal will grow like spikes, which we call it dendrites. Eventually, the spikes will be long enough to poke the membrane and cause the short circuit, which may cause fire. So when you have a phone which the battery starts swallowing, we should stop using it. That's my advice. Again, the XPS shows that when the discharge, we'll see the lithium starts depleting from the metal area to the solution. And then if we recharge, it will go back. So the peaks are changing in different directions. After normally the testing is 1,000 cycles, which is, that's normally how long the lithium battery can last. If you charge it every day, maybe 3 years, you'll find that your phone battery is not working anymore. That's because of this dendrites forming during this charging and discharge time. Another tip is, the dendrites often form when the battery is really depleted. So keep your phone charging maybe above 10% or 15%, and don't overcharge to 100%. This also can cause the different formation of the lithium. So this can help you and really make the battery last a bit longer. There's a scientific evidence here. So summary, we talk about the materials at small scales, and we know that surface can matter in the small scales. And the current research institutes, including solar cells and batteries, which are also hot topics. And with the introduction of the XPS, hopefully you can understand that it's a powerful technique for us to study the surface and help us to advance the research. So now I realize that when I took this photo 7 years ago, this model, which is representing nanoparticles, and just lying perfectly with the background where the X-ray shines on the surface and the electrons coming out and collected by the analyzer. Okay. Thank you very much for your listening, and hopefully you enjoyed today. Thank you.